Hello. In this episode of Interesting Math Problems, um, the question is find a convincing proof for the binomial expansion theorem. Now, the word convincing in mathematics just tends to mean something that makes a good bit of sense, but is not quite rigorous. Um, so yes, it's not quite a problem, but I think it's a very interesting question. You won't see this on any sort of math test or competition math problem. It's just one of those interesting ones. So, how would one go about doing this? Well, as you can see here, the sum is seemingly like weird, like what does all this mean? But it becomes apparent when you start uh, sort of just expanding sum. So let's say we have a plus b to the 0. Okay, so this doesn't make quite much sense in the theorem, but we know that that's just equal to 1. And I'm just going to write 1 here as a plus b to the first. That's just a plus b. Now, if we square it, we'll get a squared plus 2ab plus b squared. And just the final one that I'm going to show, when you cube it, you'll get a cubed plus 3a squared b plus 3b squared a plus b cubed. Okay, so you have probably started to notice a pattern, something to the likeness of, these have quite a regular pattern to them, like almost as if you add these exponents, you get this one, and that actually has a name. If you add this a squared coefficient plus this 2ab, you'll get that. So this has a name. It's called Pascal's triangle. It's quite famous in mathematics, and it has all sorts of properties. And I'll probably do a video in the future just discussing a lot of these properties. So I've just drawn out the first couple lines here of Pascal's triangle. It's infinite, so it doesn't really matter. But basically, these outer rows will start with 1, and then whenever you have an in-between space, you just add the previous two terms. So, for example, this 1 and 2 add up to this 3, this 2 and 1 add up to that 3, and so on. And you can sort of notice this pattern where it matches up almost perfectly to the coefficients of the numbers in the expansions. And another interesting property of this triangle is that it represents the choose function. Now, to those of you who are not familiar with the choose function, the formula goes such as this. So n, or choose n, or any two numbers. Typically, it could be p and q as well. So other notation for this might jog a few of your guys' memory, is r choose n, right? This is simply equal to r factorial over n factorial times r minus n factorial. So there you go. This has the unique property of actually matching up perfectly with the triangle. We start at the 0th row, and then the first row, and then the second row, and then the third row. And you'll notice that the thing, right? So 1 choose 1 is equal to 1. You can run it through here. And then another one, 1 choose, or sorry, you always start at 0. So 1 choose 0 is that, and then the next one over would be 1 choose 1. So it's very interesting that it actually does have this property. Something that we'll probably be discussing in a later video. But for now, we can sort of begin to use this information. So we know that n choose r, or r choose n is that formula down here. So you can forget about the Pascal's triangle for now. That's just pattern recognition. But what happens here is once you get this pattern recognition, you can notice that you simply put it in the formula, right? So if r is equal to 3, so that's my bad. That should be r. So, so when you're raising it to the rth power, so let's see, we can find, for example, the second term in here. We would just say, since it starts at 0 here, so we would set n equal to 1 and r equal to 3. So then we'd get 3, choose 1, times a to the r minus n, which is 2, times b to the n, which is 1, 3 choose 1, so r factorial 6, 3 factorial, over 1 factorial, which is 1, times 2 factorial, which is 2, we get 3. So then we have 3a squared b. You might notice a few changes in this in the formula. Oftentimes it's expressed with n up here, and then n over there, and r down here. And then you just flip these and flip a couple other things. So, yeah, that is how it was sort of made. But there is quite a bit more interesting proof, and I guess that's how you would use it. That's how you use the binomial expansion theorem. So, a convincing proof that I found that I quite like, you can go ahead and pause the video and sort of look for it. But there's a very interesting way to prove this, so to speak. So, I'm going to segue into a different problem here, a sort of a hint, I suppose you could say. And that is, let's say you have A, okay? A number of people, or here, I'll just start with a specific example. You have a total selection body of 10, okay? So there are 10 people, right? 10 people trying out for a job, let's say. And they'll accept 3, so 3 accepted. So a very common way that this is done, assuming that order does not matter. So basically these 3 jobs are of equal value. It's simply 10 choose 3. So that's the whole goal of this function. It's not an extension of Pascal's triangle. The whole goal of this function is to do this. So 10 people, 3 accepted. How many different ways people, assuming their people aren't the same. So how many different ways can this be expressed? Or not expressed, I guess, like how many different ways can these 10 people be accepted? Of course, 7 of them will be rejected. So this probability, or this number, is the same. And then if you could say the probability that's like 5, let's say 5 are women, like what's the probability that a woman will be chosen for the job? You would simply do like 5 women, right? Kind of lazy, I don't really want to write this all out. and then once again 3 are accepted, so the total probability, then 5, choose 3, so you do 5 choose 3 over 10 choose 3. So this is the total number of possibilities. And you can look into more of how the function works, but that's how you would go about solving that type of probability problem. And this can be used to prove the binomial expansion. So for now, I'm going to go with a narrow example. Let's say r is equal to 5, right? 5. So we'll line them up, right, in an odd way, but it helps for this demonstration. So you can set them up like this, and they're all being multiplied down here at the bottom. And we're going to look at the probability that a certain power of a will be output when you multiply this. So the question we're asking is, what is the probability that a, let's say, will come out to be the power 5? Well, the only way that a certain power of a will be 5 is if this a is multiplied by that a, is multiplied by that a, is multiplied by that a, and multiplied by the final a. So basically what happens is that is the only way. So you can sort of think of this idea as a journey, right? So we go from the a here to the a here, and it just gets multiplied down. Now, for now, we're not concerning ourselves with the idea of the whole thing expanding. We're just interested in individual terms. And you'll notice that that is the only way for a to get the power 5. Now, let's look at the how many ways a can be that a can have the power of 4. Okay, so we can, let's say, have a fun time, like go these first 4, and then for the final one, we'll just choose a b, because for each one they do have to we do have to multiply by something. We can't just multiply these first 4 because we need to choose one. So what ends up happening here is you can see that a gets this, so it's a to the 4th and b. But something you'll also notice is, well, we could have chosen this different. We could have chosen this pathway. We could have chosen to go here, then here, then here, then here, then here. And like that, you can keep going, and you'll quickly find that there is 5 total ways that you can do this. Now keep in mind that if you were to do 5 choose 4, you'll get 5. Sorry, my mouse is not the best thing in the world. Okay. You'll get 5. And if you do 5 choose 5, you get 1. Now, if we were to figure out the coefficient of this, what'll happen is the coefficient is simply because there's 5 different ways to get a to the 4th times b. It would be a to the 4th times b added up 5 times, so that's 5. And there's only one way to get a to the 5th, so you would only have a coefficient of 1. So now, let's let's continue. You would have a to the 3rd power. Well, since we have to multiply everything, now we know that b will be of the 2nd power. And so, once again, we have 5, and we're choosing 3 a's, and the others will be b's. you could think of this as there's 5 people going to a job, and they can only accept 3 of them, so the other 2 are by default not accepted. So we can go with a mundane example. And to go through all these would take forever. We can simply say that it's 5, choose 3. And that is the coefficient you'll get on a cubed b squared. So now I'm sure you guys are starting to see how this is all coming together. So this number here is always going to be what the thing is being raised to the power by. And this number here is the power of a. Okay? And because in this summation statement, typically we want a to be written first, so we want it in this type of format with a leading the charge, I suppose. So its power is displayed over, because obviously there's a b to the 5th term back here. So we could flip it around, but it's just convention to keep a in front. So that's the, I guess, mathematical way of representing this observation. So yes, that is I wouldn't say convincing proof, but certainly on the tracks to leading you to a rigorous / convincing proof of this theorem. So one thing I realized I forgot to mention, which I hope you guys didn't have to look up by yourself because I'm explaining it now, the summation statement, which simply means you go from a to r in all the integers, so you tick it up by 1, and you compute this value for all of them, and then you simply add them all up. So like the summation of n from 0 to 5 of 2x would be 0 plus 2 plus 4 plus 10. So yep, that is a proof for the binomial expansion theorem in what I hope was an original way to anything you might have seen before. Thank you for watching.